So today is really the last day that I'm going to tell you anything new. And there really isn't all that much that's new for me to cover today, but there's one kind of important thing, which those of you who had lab with me yesterday, we did it in lab, and those of you who have lab tomorrow will use it. But that's a little bit later today. There's a few things I want to go over before that. And just to give you a little more experience with seeing examples and understanding this delta G thing that I introduced last time. So this delta G0 for a reaction. So this is the way that chemists usually determine if a reaction is spontaneous or not. And it's sort of a combination of delta H and T delta S. The definition, well, it's not the definition, but it's the definition we give in general chem, is that it's equal to the delta H minus T delta S. So what I talked about also last class was that not only is it delta H minus T delta S, as you know, that's how we figure out what it is, but it's also the amount of useful work a system can do. And what I mean by useful work, as I showed last time, was chemical work, like in the body. The negative delta G of the ATP hydrolysis is what drives a lot of other reactions by coupling to them so that the total delta G is negative. Anyway, so that's one way you can think about the delta G. But for us, we really just use this equation a lot. And so what I'd like to do is talk about the roles of these two different terms, the delta H and the delta G. So the sign of delta G is so important for determining if the reaction is spontaneous, right? If the delta G0 is negative, then the reaction is spontaneous. In other words, it'll happen on its own in the forward direction. If on the other hand, delta G0 is positive, it is non-spontaneous in the forward direction. And it is spontaneous in reverse. Okay, so the sign of the delta G0 is extremely important. And by the way, when I say it's spontaneous, I mean under standard conditions. But in general chem, we don't emphasize that too much. If you're a chem major and you take physical chemistry, that will be a lot more meaningful. It's always under standard conditions. That's the only way that we know how to calculate the delta G0 in this class. We only calculate standard delta Gs, and so it's only valid under standard conditions, which are 1 atmosphere pressure and 1 molar of everything in solution. Like I said, that's not too important in our class. So let's think about the signs of delta G. And so what I want to do is, like, for example, suppose we have a reaction that has a negative enthalpy change and a positive change in entropy. Okay, so if this guy here is negative, that is going to contribute to making delta G0 negative. Okay, so this contributes to making the delta G0 negative. So we could say that it contributes to making the reaction spontaneous. But when we take a look at the delta S here, all right, so here's delta S being oh yeah, all right, so this is no but. This does the same thing. if delta S is positive, that means that minus T delta S is negative. And this means that the positive delta S, this contributes also to making the delta G0 negative. It contributes to the spontaneity. It contributes to the reaction being spontaneous. If one of these had a different sign, then it would contribute to the reaction being non-spontaneous. So in this example, when you have a positive delta S and a negative delta H, we know that delta G0 will be negative. There's no positive term. And as you could see that the positive delta S, when you multiply by minus the temperature, you're changing the sign to be negative. So the sign of the delta S will always get, that term will be, that minus T delta S will obviously have a different sign than the delta S. Okay, but what I want to point out right now is that there are actually 4 different possibilities of combinations of delta H and delta S. Clearly, we can have the delta H0. We can have delta H0. So here's one of them, the one we just did. Delta H0 is negative, delta S0 is positive. That's the example we just did. And what we saw, that this being positive, this will be negative, and the delta H is negative. So what can you say about a reaction that releases energy? So this is an exothermic reaction where there is an increase in disorder. And when you have a reaction like that, that reaction will always be spontaneous, at least under standard conditions. That the temperature will certainly not influence this. So the reaction will simply be spontaneous. And what happens, and that makes sense actually, because here's your system, okay? The system is releasing heat. I know that because the delta H is negative. So the system releases heat. So that means that the delta S surroundings is positive. But at the same time, what's going on in here is that there is a greater amount of disorder or energy dispersal in the system. The delta S is positive. So you have a positive delta S surroundings and a positive delta S. So that means that the delta S total is positive plus positive, right? It's 2 of them. Delta S plus delta S sir, both contribute to making this a spontaneous process. And that's the same is true here. This helps make the delta G0 negative, and this does too. The next example is similar, but okay. So we have, if delta H0 is positive and delta S0 is negative. So here, again, we have our delta G is delta H minus T delta S. And so we're going to analyze the signs once again. If delta S is negative, all right, then negative T delta S will be positive, and delta H0 is positive. So now we have an endothermic reaction where we have a decrease in disorder, I meant to say in the system. We have so an increase in order. Okay, so what happens is that delta G0 is positive. This will be non-spontaneous. And if you look at it, there's no way, the temperature is always going to be positive. So there's no way we could change that with any change in temperature. This reaction will be non-spontaneous at any temperature, just like this one here is spontaneous at any temperature. Okay, and we have a sort of a different but similar drawing right here. We can look at it from the point of view of the entropy of the system and surroundings. Here, we have heat going into the system because it's endothermic. What does that do? What does that make the delta S surroundings? Is it going to be positive or negative as you take heat away from the surroundings and put it in the system? What's the sign of that delta S surroundings going to be? You're taking away heat. Negative, right? Because delta S sir is proportional to the heat. If you're taking away heat, it's going to be negative. And we're creating order. So less disorder. Delon, I heard that deep sigh. I heard it. Yeah. Sorry about that. Anyway, so delta S sir is negative, and with the creation of order in the system, we have a delta S that's negative. So delta S total will be negative. And that goes along with a positive delta G. Okay, positive delta G, the reaction is non-spontaneous. Delta S total negative, non-spontaneous. No matter which way you look at it, if the sign of the delta H is positive and delta S is negative, that reaction is never going to be spontaneous. You're going to have to do something to get that reaction to go, like supply it with energy. All right, so that was the second case. Now we have the third case where let's suppose we have a negative delta H and a negative delta S. So when these two are the same sign, because in the delta G relation, you have a negative sign here, whenever these have the same sign, they will have, these two terms will have opposite signs, which is not what happened in the first two examples, but it's what happens here. So here, if you have a negative delta S, that leads to a positive contribution to the delta G. So this contributes to delta G0 being positive. However, the delta H is negative, which obviously contributes to the delta H being negative. To the delta G being negative. And so we have two competing terms here. You can call it that. So will a reaction like this, will a reaction with a negative delta H and a negative delta S be spontaneous? So this is an exothermic reaction in which there is an increase in order or a decrease in disorder. So what's happening is that the release of heat, the Q going into the surroundings, means that delta S surroundings is positive. However, there is more order in the system. So delta S is negative. So the sum, which is delta S total, I don't know what it is. Will this reaction be spontaneous? It depends. Same thing here. It doesn't matter which way you look at it. It depends. Well, what does it depend on? So here you have a negative term, and this is negative, so this is positive. Well, what it depends on is the size of these two terms. One of these terms is going to be bigger than the other. So it depends on the sizes, or I call them the magnitudes, of these two terms. Okay, so if the delta H term, well, let's put it the other way. if the T delta S term, so this is the magnitude of the minus T delta S term. If that is greater than the delta H term, then what's going to happen? If this is the larger magnitude term, and this is a positive, right? Then the delta G0 will be positive, and the reaction will be non-spontaneous. Well, I don't want to confuse the issue with this negative sign here. So I could say, minus T delta S is the same as T delta S if you're taking the absolute value. Okay, so if this is a greater magnitude term, it will be non-spontaneous. Well, when will that happen? Well, of course, it matters what the temperature is. So at high temperatures, this magnitude will be larger and it will become greater than the delta H term in magnitude. So at high temperatures, this is the dominant term, the T delta S term. So this term is the dominant one. And then what happens is, of course, that the delta G0 will be positive because that term contributed to making the free energy change positive. Okay, so that's what happens if the temperature is high. If we look at this again and we say, well, what if the temperature is low? If the magnitude of this term is smaller than the delta H term, then the delta H term is going to be dominant and the delta G0 will be negative. So on the other hand, if T delta S is greater than delta H, less. The delta H term is the dominant one. And since the delta H is negative, the delta G0 will be negative. And the reaction is spontaneous. When does this happen? It happens if T delta S is less than delta H, which happens when the temperature is low. So it happens at low temperatures. So basically we have this situation. If we look at what happens to the free energy change as we increase the temperature, we see that it goes from being let's see, let me just make sure I'm getting this right. So at high temperatures, when this term is dominant, it's non-spontaneous because this is positive. So it'll go from being spontaneous at low temperatures to non-spontaneous at high temperatures. So as the T goes up and you increase the magnitude of this term, the reaction becomes more and more non-spontaneous. So there's going to be a temperature somewhere in here, which I call the crossover temperature. There's going to be some temperature where the reaction goes from being spontaneous in this case to being non-spontaneous on the other side. When does that happen? Well, we're using this formula over here. So what happens is it goes from delta G0. So at low temperatures, you have delta G0 is negative. At high temperatures, delta G0 is positive. Well, when delta G0 is 0, we can solve for the crossover temperature. So that's what we'll do. And then I'll just move the T delta S to the other side. and I can solve for the temperature. This is the crossover temperature. So it's actually the delta H divided by the delta magnitude of the delta H. Well, they're either both positive or both negative, so it doesn't much matter. So if you actually take the delta H for a reaction divided by the delta S, notice you'll have units here of kilojoules per mole. Here, you'll have to convert this. Normally, these are on joules per Kelvin mole, but you'll have to convert it to kilojoules per Kelvin mole. Either that or you have to convert the delta H to joules per mole. And you'll notice everything is going to cancel, and you're going to end up with Kelvin units here, which is good because you want to solve for the temperature. Okay, so I want to get back. Let's see, where was I? So the example I was doing at the end of class, the end of the last class, I was working on activity 4. And it was this, remember that reaction was the ethanol liquid plus O2 gas giving me acetic acid plus water. Okay. And this was liquid and liquid. And what we found last time was that the delta H0 for this reaction was really large negative number. Okay, and the delta S for this reaction, this is from last class, is negative 136 joules per Kelvin per mole. Okay, and we found out that at 298 Kelvin, 25 degrees C, that if you take this delta H minus 495.1, so now we formulated the delta G, minus T, which is 298 Kelvin, okay? So this is delta H minus T, delta S. And now I'm going to convert this to kilojoules per Kelvin per mole. Oh, this thing doesn't work right. Okay. And minus 0.136. And so this is negative 495.1 plus 40.5. So this temperature, 298, is low enough so that this term here is smaller in magnitude. So T delta S is less than the magnitude of the delta H here, which is 495. And because the delta H is the dominant term, and because the delta H is negative, that will end up making the delta G 0 negative. So when you add these two together, you get 490. What the heck? Oh, I just didn't do it. I have to do it. 490. We did it last time. Comes out to, oh, that's not right. Yeah, I think it's 450, negative 455. I may not have copied those numbers right. We did this last time. So you have a negative delta G because of the fact that this term is bigger, all right? But you have to ask yourself the question, you know, here at this temperature, T delta S, the magnitude is less than delta H. But as the temperature increases, it's going to increase the size of the T delta S term. So T delta S term will increase. Okay, and eventually the T delta S term should dominate. the picture. So we expect that at high temperatures, you're going to have a non-spontaneous reaction. So when is this going to happen? What is the crossover temperature? Do we really have to worry about this? Well, let me show you what the temperature turns out to be. If you take the magnitude of delta H divided by delta S, that's 495.1 divided by 0.136. These are both negative, so the signs don't really matter, but they never will with the absolute value. And that comes out to 3,639 Kelvin. Well, that's really high. So above this really high temperature, the reaction would be non-spontaneous. But let's think about what's going on in this reaction. You know, we have ethanol, liquid, plus oxygen gas. Well, oxygen will be fine at 3,600 Kelvin, but liquid ethanol, no way. First of all, it'll evaporate. Second of all, it'll decompose. It probably won't exist anymore in the same way. So, and the same thing goes for acetic acid as a liquid, which is completely evaporated, and so will water, and probably won't exist in the same way at those high temperatures. So really, for all intents and purposes, you'd have to get above an extremely high temperature for this reaction to be non-spontaneous. But still, it probably everything will be decomposed in this example, all except the O2 would decompose. It's so hot. But theoretically, the reaction would become non-spontaneous. So if you draw a little line here, you would have it being spontaneous. At lower temperatures, it will go to be non-spontaneous at higher temperatures, and that crossover point is 3639 Kelvin. Yeah, which is pretty hot. All right, so basically when you have the delta H and the delta S that have the same sign, when you multiply the delta S by negative T, you're going to have two terms with different signs. And then the spontaneity is going to depend on the temperature. So that's the one thing I wanted to tell you today. So be careful. If the delta H and the delta S have the same sign, the spontaneity will change with the temperature. And for one of them, it'll go from being spontaneous to non-spontaneous, and for the other, it'll go the other way. So you can look at those examples that I went through. So there's only one more thing, one more important thing that I need to tell you about. That's really the last topic in this unit. And that is that this delta G0 is closely related to the equilibrium constant. So first, I'd like to argue why this would be the case, all right? Why would these be related? And so if you think about it, if you have a reaction, so if a reaction has a negative delta G0, okay, so that means it's spontaneous in the forward direction. That means that the products are favored. There will be more products at equilibrium. So a negative delta G0 correlates with a large K. And what I mean by that is a K that is greater than 1. Okay. And the larger the K, the more negative the delta G0. So there is this correlation between negative delta G values and K's greater than 1. And it makes sense because a negative delta G favors the products because the reaction is spontaneous in the forward direction, and a large value of K favors the products. which brings me to something I wanted to tell you about, because some of you are not writing your equilibrium constants correctly. Many of you are taking the products and putting it in the denominator. And I saw that on the test. I would say at least 10 people did that on the test. So please don't forget that if you have a reaction, 1A plus 2B goes to 3C, that the Kc anyway, would be concentration of C cubed over AB squared. I don't want to see it the other way. It's going to totally screw up your answers on the next exam if you don't know how to write your equilibrium constant. It's products over reactants. And so if K is greater than 1, the products are favored. That means you'll have more products at equilibrium. And that goes along with a negative delta G0. So there's this correlation, and that correlation isn't there if you're writing your K in the wrong way. So please be careful not to do that. So write your K as sort of an aside. Okay. So the other thing, of course, that can happen is that, so what if a reaction is non-spontaneous and we have a positive delta G0? Well, that goes along with a K value that's less than 1, right? This means it's not spontaneous. It's actually spontaneous in reverse, which means the reactants form, okay? Which means, the reactants are favored, which is true of K being less than 1 because reactants are in the denominator here. If they're greater than the product concentrations, then you'll have a value of K that's less than 1. So a delta G0 that's positive, I'll write positive delta G0, correlates with a K that's less than 1. Okay, so there is actually a mathematical relationship that I'm going to tell you, and it's pretty simple, between the delta G0 and the equilibrium constant. It could be a Kc, it could be a Kp, it could be a Ka, any of these ways, any of these equilibrium constant for different situations. And this mathematical relationship keeps this same correlation. Using this, we have this characteristic of this equation. If the delta G0 is negative, it goes with a K that's greater than 1. If the delta G0 is positive, it goes with a K that's less than 1. If the delta G0 is 0, which we've never run into because we've never had reactants and products with the same delta G, but if we did, it wouldn't favor reactants or products, and the K would be equal to 1, right? Your products of reactants would be 1. So what is this mathematical relationship that sort of magically puts this all together? And here it is. It's delta G0 is minus RT times the natural log of K. Now, delta G0 we usually want in kilojoules per mole. So that would mean that we would use R. This is, again, the gas constant, but we'd have to use it in kilojoules per mole Kelvin, so that when we multiply by the temperature in Kelvin, right, we're going to get a cancellation there. And the log, let me call this KEQ so that we don't get it mixed up with Kelvin. Okay. Okay. This is temperature. Okay, so when we do this, the Kelvin units will cancel and we'll have kilojoules per mole. And that's, that's what we want the delta G to be in. So if you think about this relationship, if this K is greater than 1, then we have the log of something that's greater than 1. The log of something greater than 1 is always positive. Temperature is always positive. The gas constant is positive, but this sign here, if you multiply negative times all these positives, you'll have a negative value. So you end up with a negative delta G zero. Okay. On the other hand, if K equilibrium is less than 1, the log of something less than 1 is negative. Okay. And so you have a negative times temperature, which is positive, times R, which is positive, times a negative. Negative times a negative is a positive. So delta G zero is positive. And the last thing is if K equilibrium is equal to 1, then this log, ln of 1, is 0. And so delta G zero is simply 0. So this mathematical relationship is very, it very concisely relates these two things together. And, if you don't know where it comes from, at least, and why it works, which if you want to learn about it, we learn about it in PChem and Chem 405. If you're a Chem major, you will have to take that course. Anyway, it's pretty cool because it makes sense, something that favors the products, K is greater than 1, delta G is negative. Favors the reactants, K is less than 1, delta G is positive. So, so this is very handy. So if we're given a K equilibrium, either a Kp or a Kc or whatever, okay, we can calculate a delta G zero for that reaction at the particular temperature that the K is given at. Okay, so let me show you just an example of this. So for example, supposing we have a very large equilibrium constant, pretty large, 10 to the 5th. Let me show you how to use this equation, minus RT log of that number. So it's minus 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. Temperature, generally 298, unless I specify otherwise. And there are some, on the exam, I do have, I think in one problem on each one, I have a temperature other than 298. Be careful of that. The log of 1 times 10 to the 5th. And that is, let's see, you notice it's positive because that number is greater than 1. So you put that together, you're going to end up with a negative sign because there's no other signs here. So this comes out to negative 28.5 kilojoules, okay, per mole. Kelvins cancel. Okay, so that's your delta G zero. And it makes sense, it's negative. It favors the products, and K is greater than 1. Okay, and the greater the value of K, the more negative the delta G will be. All right. So what if, here's another example. What if K is 1 times 10 to the negative 5th? So the only difference would be that this would be negative 11.51. So delta G zero is minus RT log 1 times 10 to the minus 5th. So this would be negative 11.51. Multiplied by everything else, it comes out to positive 28.5 kilojoules per mole. So you could see that you have K being less than 1. You have a delta G zero that's positive. Okay. Okay, so you can also use this equation in reverse. So once, you know, we have a relationship between delta G0 and the K, we can manipulate it. We can divide both sides by minus RT, and these will all cancel out. And we'll have the natural log of K is delta G0 minus delta G0 over RT. And now we can, how could we solve this equation? Anybody? What can we do to? Oh, Ashley asked me a question a long time ago that I never answered. I'll have to answer that later. So what's going to happen here? How am I going to solve this? How am I going to solve for K? Raise E to it, basically. Okay. So basically, we're going to take E to both sides, which is the same as doing the inverse log. So E to the X is inverse natural log. So I could write E to the minus delta G0 over RT equals K. I could have as easily done inverse natural log is the same thing, minus delta G0 over RT equals inverse ln of K, which is just K. Okay. So we have to be careful with the signs here, because sometimes sometimes we have, you know, let me just show you an example. So suppose that our delta G0 equals 100 kilojoules per mole, positive 100. So E to the minus 100 kilojoules per mole divided by, my nose is so itchy, 8.314. I think it's the hair. I'm not used to this long hair. 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. Oh, I don't know why I have all these parentheses. Times 298 Kelvin. So what does this come out to? If we just do this exponent here, it turns out to be negative 40.36. That is a big negative exponent. Some of you on your calculators will have to do inverse ln negative 40.36. This negative sign comes from the fact that there's a negative sign there. The delta G0 is positive. If it were negative, you'd have to cancel those negative signs. I'll show you that next. So look at this number that comes out here. This K is 3 times 10 to the negative 18, right? That is tiny, very, very tiny. So that basically says this reaction pretty much doesn't go forward at all. That the reactants are heavily favored. So when you have delta G's in the hundreds, 300, say positive 300, that would be like the reaction doesn't go forward at all. So there's all different degrees. Let me just do one example with a negative delta G. If delta G0 is negative 10, so that is a pretty modest negative number. It's not negative 1,000 or 100 or something like that. So here I want to find the K. So again, it's E to the minus delta G0 over RT. So let's figure out what minus delta G0 over RT is. It's minus 10 kilojoules per mole over 8.314. Sorry, minus 10, right? So I make that mistake too. So be careful. Okay, so this is actually going to be positive 4.04. See, it's a much more modest number. And this comes out to 56.6 as the equilibrium constant. So yes, the products are favored. But this reaction isn't necessarily going to completion. That number isn't 10 to the 5th or 10 to the 3rd or something like that. Products are favored. Delta G0 is negative. So products are favored somewhat. Delta G0 is a modest negative number. Okay, so there's all different magnitudes of these things that can happen. So last time I did that activity 4, numbers 1 through 4. And now I'm going to do activity 4, number 5, which is the part of the problem that relates the delta G0 to the K. Okay, so that's up next. Get that, pull that problem here. Okay, this is activity 4, number 5. Okay, so we basically have done everything else, and now we're going to calculate. We're given the delta G0. Well, we figured it out last time. It's 454. I think I used 455 earlier, but that's okay. So here is the delta G0. That is a big negative for a delta G. So what do you expect that the K value? It's going to be a pressure equilibrium constant. Remember, it had only one gas. Actually, what is the expression for Kp for this reaction? These are all liquids. So what's the only thing that appears in the equilibrium constant?
Oxygen.
And where is it? Is it in the numerator or in the denominator? It's a reactant. Remember, K is products over reactants. So it's in the denominator. Oh, that's right. So it's just 1 over PO2. That's a weird looking equilibrium constant, but that's what it is. Okay. So actually, when we're done, we're actually going to find what the partial pressure of oxygen is at equilibrium, because all we have to do is solve for it. PO2 is 1 over the K, whatever that is. So they're related inversely in this crazy case, in this particular case. So delta G0 is minus RT log of Kp. So we know that delta G0 over minus RT, that E to that is going to be equal to the K, which in this case is Kp. All right, so let's do it. We have negative 454 kilojoules per mole. That's delta G. Take the negative of that and divide it by RT. And that comes out to 183. So we have E to the 183. Yeah, this is so large. This is, I don't even know if your calculator can do this. 183. Yeah, it comes out to 3 times 10 to the 79th. If ever a reaction has gone to completion, it's pretty much this one, okay? So this is basically goes to completion, because the K is huge, okay? So what does that mean about the pressure of oxygen at equilibrium? So here's the reaction again, right here. So if this reaction is going all the way to the right, pretty much, then there's not going to be any oxygen left at equilibrium. And in fact, like I said before, they're related by this inverse relationship here. Okay, so basically, wow, how did I screw that up? Oh well. So So this is K. So K is 1 over the partial pressure of oxygen, which means that the partial pressure of oxygen is 1 over K, which is 1 over 3 times 10 to the 79th, which obviously is going to be a very small number. And in fact, it is 3 times 10 to the negative 80th atmospheres. So that is so small that there is no way you could measure that. In fact, the only way to really know that number is to measure the delta G zero by some other method. Then you could sort of figure out how low that pressure is going to be. So without knowing the delta G, you'd never be able to figure out. You'd never be able to measure that equilibrium constant. You'd have to figure out another way. So how are you doing, people? Everybody hanging in there? You want a little break or what? So I'm going to, because what I have to do is just a couple more problems, really, of doing examples so that you'll be more prepared to do some of it yourself. Okay. So let me, let's see, where's my, here it is. So here's the next problem. Just more on free energy. I love this reaction. I use this reaction in PChem a lot, and I've used it in this class before. The N2O4 reaction to form NO2. I could write it either way, but here I've written the N2O4 breaking up into 2 NO2 molecules. And so what you're given in this example is you're given the free energies of formation. So you could calculate the delta H from that. You're also given the entropies, the standard entropies for each of these. And you're asked a pretty big question here. You said, what is Kp for this reaction at 298 Kelvin? But this is not a one-step problem. So you're given the delta HF zeros. You can use that to calculate the delta H. You can use this to calculate the delta S, right? But that still isn't going to give you the Kp, the equilibrium constant. What are you going to have to calculate? Well, of course, it says it right here. You need to find the delta G. So the way to handle this is to get your delta H, your delta S, put them together and find delta G. Once you have delta G, you can find the equilibrium constant. And so that's what this example is all about. So the first thing I'm going to do is just start with the delta H. So what is my delta H0 going to be? It's going to be 2. Remember, it's products minus reactants. If you give me reactants minus products, you will have calculated delta H for the reverse reaction, and all your answers will be wrong. Okay. So please remember to do products minus reactants. So NO2 is the product. It's 2 of them. So 2 times 33.10 minus 1 times 9.08. And that comes out to 57.12 kilojoules per mole. So that is the delta H0 for this reaction. Okay. Similarly, we can calculate the delta S. If we calculate the delta H, by the way, this is positive. So this is an endothermic reaction. Requires heat. Actually, can you think of a reason why it would require heat? Because this is, this is the end of the course, and we try to put a few things together here. Why do you think, why is it exothermic? Why does it release heat? And that's something that, you have to really think about this. If you have N2O4, it looks something like this. So that's what you start with, and you end up with 2 NO2s. And I draw it like this because that emphasizes the fact that you have broken this bond. And that's about all that you do in this reaction. Yes, the N2O4 molecule is being broken apart, and it requires energy to break bonds. So it is really not surprising. So it makes sense that the delta H here would be negative. Positive, I mean. Makes sense for delta H to be positive. Energy is required. Okay, so now let's calculate the delta S0. Okay, so delta S0 is so here's, we have 2 times the S0 of NO2 minus 1 times the S0 of N2O4. So using those numbers that were given here, 2 times 239.9 minus 1 times 304.3. Now, before you do this calculation, before you put it in your calculator, you should be able to figure out what this sign is. What should the sign of the delta H for this reaction be? Should it, you know, what were the guidelines? Remember, these are gas molecules. We start with 1 mole of gas. We end up with 2 moles of gas. So the delta S is going to be what?
Positive.
That's right. This is positive because we gained 1 mole of gas. And gases are better able to spread out thermal energy to disperse heat. So more moles of gas, more of an ability to disperse heat, which is what entropy is all about. So more moles of gas, more dispersal of heat, greater entropy. And so you have a positive sign here. Again, it's always products minus reactants. We're taking the final minus the initial. So we have our delta H0 and delta S0. And now, since we're trying to get the equilibrium constant, we need to figure out the delta G0. If I forget to put the temperature in a problem, you can assume it's 298. In this problem, looks like it doesn't, well, it doesn't, oh, it does say it right here, 298. Yeah, okay. So here, we're going to take our 57.12 minus 298 times, now, I can't put 175.5, right? I need to convert, because this is 57.12 kilojoules per mole, 298 K. Now, it has to be 0.1755. You have to divide by 1,000 to get kilojoules. So this is kilojoules per mole Kelvin. Kelvins cancel. And you end up with, let's just actually, this is 57.12 minus 52.3. So you have 2 competing terms here because we have a delta H that's positive and a delta S that's positive. So this is a negative term here that's competing with this positive term. And which of these is going to dominate? Well, like it depends on the temperature, but you could see that at 298 Kelvin, these 2 terms are close to one another in magnitude. but the delta H is somewhat larger in magnitude. And so the delta G0 will be negative at 298. And it comes out to 4.82, but it's nothing really too big, is it? So what happens if the temperature goes up? What's going to happen to the delta G? So if the temperature were to be higher, delta G0 would become negative. Okay, but we're not up to that part of the problem yet. We're going to do that next. For now, we're going to find K, which is Kp, which is actually the concentration. Well, let's just call it what. Let's just calculate it. E to the minus delta G0 over RT. First, let's calculate this exponent. Negative 4.82 kilojoules per mole divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin times 298 Kelvin. And so we're going to do, this comes out to negative 1.95. The next line. So K is e to the minus 1.95, or inverse natural log of negative 1.95, which is 0.143. Okay, so it's less than 1, but it's not negative 10 to the negative 5th. So it's modestly less than 1. So there actually will be both NO2 and N2O4 present at equilibrium. Okay, so
Question.
Yeah, please.
Does it doesn't matter that those units were kilojoules?
The kilojoule units cancel here.
Oh, okay.
It does matter. I mean, you couldn't use, if you used 8.314 without the 10 to the minus 3, then this unit on the bottom would be joules and not kilojoules, right? And then you would have a mixed up, then you would get the wrong answer. You know, you would end up dividing by a much larger number. You would have a much smaller delta G over RT. You know, it would change the value of K a lot. So that's why it's really important to make sure that if you're using a delta G that's in kilojoules per mole, you have to use the gas constant in kilojoules per mole Kelvin.
Okay, thank you.
Just be careful, yeah. So, it says, does the value of Kp and the sign of delta G, do these values imply that the reaction is spontaneous or not? And how do the different terms contribute? So first of all, we have a Kp that's less than 1, okay? And we have a delta G0 that's positive. And this correlates. You should take a look at that, you know? If you do a problem and you had a positive delta G, but you end up with a K that's greater than 1, oh, you should start scratching your head about that. It's not, doesn't make sense, because a negative delta G, a positive delta G means spontaneous in reverse. It favors the reactants. You should have a K that's less than 1. So is this reaction spontaneous or not? The reaction is not spontaneous at 298 Kelvin under standard conditions. And how do the terms contribute? So I kind of talked about this already, but I'll put it down again. This is 57.12. This is 298 times 0.1755. Remember, the delta S was plus 175.5 joules per Kelvin per mole, which is 0.1755 kilojoules per Kelvin mole. So when you multiply this together, you get kilojoules per mole, and that is 57.12. Sorry, this is minus, wait a minute. No, sorry. Minus 52.3. There it is. I only got the right number. Okay, and so this comes out to be 4.82, like I said. I think that's what it was, right? 4.82, okay. So it's positive. So the reaction is not spontaneous. The delta H contributes to the reaction being non-spontaneous. But the negative T delta S term contributes to the reaction being spontaneous. So there are two competing terms, and you can see that the delta H term wins, and the reaction is, so this one wins at 298. Okay. But how will temperature affect this equilibrium? It will definitely affect this equilibrium. Delta G is delta H minus T delta S again, because this is positive and this is positive, this term is negative. Okay, so what's going to happen is as the temperature goes up, the negative T delta S term grows in magnitude. Oh. So eventually, this negative will dominate. Eventually, this term dominates, and delta G0 becomes negative, and the reaction becomes spontaneous. Okay. So here's another approach. Rather than just finding the crossover temperature, suppose you estimate what delta G is at 400 Kelvin. It's just using the same equation. So we have what these numbers are for the delta H and the delta S. And the reason this is an estimate is because they do depend somewhat on the temperature. And we're going to pretend that they don't. That's why I call it an estimate. So this is 57.12 minus, so at 400 Kelvin, instead of putting a 298 here, I'm putting a 400 multiplied by the same 0.1755 kilojoules per Kelvin mole. This is kilojoules per mole. Okay, so now you can see what's happening here. This is the same. The delta H isn't changing, or not much. And in freshman chemistry, we never consider that it's even changing. But this guy here, instead of being negative 52.3, it's negative 70.2. So that when you add these up, you actually get a negative number as the delta G0. So now the delta G0 is negative. So this is spontaneous. So what would happen if I found the K? So before, when I found my K, I had e to a negative power. Now, because the delta G0 has become negative, it's going to be e to a positive power. And so the K is going to be greater than 1 instead of less than 1. Well, I'm not calculating that, but that's what would happen. So this reaction has gone from being non-spontaneous to spontaneous by changing the temperature. So as the temperature goes up, it goes from non-spontaneous to spontaneous. And again, you could think about it as you have these two contributions. This is positive and positive. Oops. Okay, so as the temperature grows, as this T goes up, this term becomes more important. And eventually it will dominate. And it leads to spontaneity at high temperatures. So it goes from non-spontaneous to spontaneous. So what is the crossover temperature? We always calculate this the same way, the delta H over the delta S. It came from figuring out when is the delta G equal to 0. And in this case, and again, you have to be sure to use everything in the same unit here. So this is kilojoules per mole Kelvin and kilojoules per mole, and the units are going to be Kelvin. And it comes out to 325.5 Kelvin. Okay, so you could see that at 400, you're higher than that crossover temperature. So the reaction has gone from being non-spontaneous to spontaneous. This is 325.5. Okay, so above that temperature, the reaction, the delta G 0 will be negative. Below that temperature, the delta G 0 will be positive. So I hope that that's, you're grasping that. Anybody have a question or anything? So there's just one other little thing I wanted to show you. Oh, this is later. We'll do some course evaluations, but I wanted to go over one more thing first. Did you guys get this email, by the way, about the course evaluations? It came on April 21. There was an email. It's a long time ago already. So if you look on April 21, there's an email from the Rick Department of Physical Sciences about this course. And we're just asking that you don't forget to do this evaluation. And the deadline is May 4th. Okay, but let me do what I was going to do, which is talk about one more thing. Somebody says, oh, you did. I see a lot of yeses too. I thought there was just the one no. Kayla, I bet you got it and you just didn't notice it. All right, so there's another type of problem. And there is a problem like this on the exam. It's really along the exact same lines, except that instead of giving you the equilibrium constant, it gives you the pressures. And you have to figure out the equilibrium constant, which is, that's what we did in the equilibrium unit. So it's not so strange. But suppose you have the same reaction and that you're given the partial pressure of NO2 and the partial pressure of N2O4 at equilibrium. So this allows you can use this to get the pressure equilibrium constant. And then you could use that to get the delta G 0. And so that's another kind of sort of a version of these types of problems. So I'm going to give an example to you. Supposing I tell you that the partial pressure of N2O4 is 0.386 and that of NO2 is 0.235. So what would Kp be? So it would require you to remember that you have to take the products over the reactants raised to their proper stoichiometric coefficient. So you would have to put 0.235 squared over 0.386, and that would give you the value of Kp, 0.143, okay? And let's just say it's at 298. If you're not told, then it's definitely 298. So then you could calculate the delta G0 from that, from minus RT log of K. And you would simply use the 8.314 that we've been using. That's kilojoules per mole Kelvin, 298. And then the log of that 0.143, which is less than 1. So this is going to be negative. That log of 0.143 is negative 1.945. So when you put all this together, notice you have a negative and a negative here. So you're going to get a positive delta G0, which makes sense because you have a K that's less than 1 that favors the the reactants. And delta G0 should be positive, and it's going to be because we have two negative signs. Okay, so that comes out to a positive 4.82, which is of course the number that we used before, but maybe you don't remember, but anyway. So we do have a positive delta G0, which correlates with a K that's less than 1. And so that makes sense. All right, so that's just another kind of problem that you could be given. Here's another little thing I could ask. You know, here we're dealing with this problem. And the delta S0, I could say, well, what is the sign of the delta S0? So suppose you know, here's delta G is delta H minus T delta S. So you're gaining a mole of gas, so it should be positive, right? Because the moles of gas is increasing. So that means this would be positive and this would be negative, okay? Just put it on another page. So we just figured out that this is positive. So suppose you knew delta G was positive and this term is negative. If I ask you, what has to be the sign of the delta H0? You know, if you didn't know how to figure out that you're breaking a bond, you take a look at this and you go, oh, well, if this term is negative and the delta G0 is positive, what does the sign of this have to be? It has to be positive. And that's because otherwise the delta G0 could not be positive. Because the delta S is positive, which makes this term negative. All right, I think that's enough. That's really all. What I'm going to do is, well, we're actually asked for you to figure out, to give you time to do this evaluation in class. I don't know. I don't know if I care if you do it in class or not, but I think it's good if you do it. But anyway, I don't have anything else to say today. Monday, we officially have class, and I'm going to use Monday for kind of a, I'm probably going to go over one more problem. So Monday, I'm going to go over one problem, and I'm going to take questions. And you could ask me questions about the exam. That's fine. I'll answer them as best I can without giving away the answers. So that's what we're going to do Monday at 2. What else is? Oh yeah, I'm giving out an exam tomorrow. You know, I know it doesn't give you a lot of time to digest this material, but you will have until, you know, the following weekend to do it. I don't think there are many graduating seniors in this class. I asked people and I'm getting pretty much no's. There might be one person, so it's okay if you were to hand it in a little bit late, but try not to hand it in too late, because I do have to grade them and it takes me a while, as you know. So I'm going to give the exam out tomorrow. It'll be due Friday, but let me know if you have some kind of situation and you can't get it in. All right. Yeah, the exams will be out tomorrow, but probably not until late in the day. Yeah, I'm going to try to make a list like I made before. But you know, there are only 3 classes on thermo and we did a lot of overlapping things, so it might not be quite as useful. How many questions, you know how these thermo problems are, like they have A, B, C, D, and E, that kind of thing. So I think that I'll probably have 3 thermo questions, which are each about a page long with all the spaces. And then there'll be a buffer problem and then maybe another acid problem. I'm not sure. I'm pretty sure, but yeah, maybe. But I'm going to say 5 or 6 problems, but you know, of course there'll be parts in these problems. So yeah. Yeah, not this Friday, Morgan. Come on. When have I ever asked for a test in one day? Yeah, no, next Friday. Yeah. Oh, any other? Ashley had a question. What was that question?
It was from a long time ago. It's okay.
It's a galaxy far, far away. Hold on. Oh, I don't know. Oh, there it is. Yeah, an exothermic reaction is an increase in disorder in the surroundings, in a sense, because you're putting heat into the surroundings. But you can have an exothermic reaction that increases the order or increases the disorder in the system. If you have a, yeah. So
is that why for number
in other
3?
words, the sign of delta S and delta H are unrelated. All right. Delta S depends on the order or disorder in the system. And that depends on the reacting chemicals. Okay. Delta H is whether heat is released or absorbed. And that determines the sign of the delta S surroundings, not the delta S system. Do you get that?
Yes, thank you.
Because like, I think I did an example where we created order in the system, which you would think, oh, you can't, delta S is positive, that's negative, that won't happen, but it will if delta H is really big and negative, because it means you have a larger increase in entropy in the surroundings. So anyway.
Professor, were you ever able to answer my question about when it's a warm room, but the
Oh, you know, I was right with what I said. It was that, so basically, I think what it is like you think it's cold, but your hand is not really sensing the temperature of that table. It's sensing the flow of heat. And because that glass has such I think it has a small heat capacity, which means it doesn't retain heat very well, that heat flows through it very fast, that you're feeling that change in temperature. Apparently your body is not really that good at sensing temperature. So that table is really not as cold in terms of its temperature as it appears to be. Anyway, I read a little bit about it, but I didn't read a whole lot about it. But it doesn't violate the laws of thermodynamics. It has more to do with heat flow. I'll try to read a little bit more about it and let you know. But I was, yeah, it has more to do with the heat capacity, the ability of a substance to store heat. And apparently you can't detect the temperature. So you think it's cold, but it's really not. Anyway, that's what
All right. Thank you.
Sorry, I couldn't do better than that. Yeah, do these evaluations. You'll make me look bad if no one fills them out. So plus I would like to know, to tell you the truth. Oh yeah, Tyler, I have to put that. I missed that for a couple of people. Did you check right away? Because later I changed some of those. I can check that. Yeah, no, it's going to be the one I told you it was going to. Okay. Okay. Well, I checked it later, but maybe I missed you. That's all right. I'll fix it. I'll fix it right now after class, as soon as everyone says goodbye. Then you can check it again. And if it's not right, just email me, okay? Okay.
Thank you, Professor.
Thank you. Thank you. Yeah.
Bye, Professor. Have a good one.
Yeah, have a good one.
Have a great day, Professor. Enjoy the weather.
Oh, yeah, thanks. Actually, a former student is coming by. I haven't seen in a while, so that's
Oh,
nice.
that's nice. That's nice. Catch up. Have a great day.
Me too.